Hello, and welcome to this video about rational numbers. In this video, we'll show how the rational numbers are constructed from the integers, and then show that this set of numbers is a field, and then that it's an ordered field. So this is how we'll represent this type of number, as an ordered pair of two integers, shown here to be a and b is never equal to 0. And this is the number in terms of how we would normally write a rational number, that is, as a fraction. And in this case, a can be bigger than b, and a and b don't have to be coprime, and can be a fraction that hasn't been reduced to its simplest terms. And we'll use this equivalence relation to help construct this number. So whenever this equality is true, then this equivalence relation is true. This ordered pair will represent these fractions here, and we'll define addition, multiplication, and this equivalence relation on the behaviour of these fractions. We can see here that if these two fractions are equal, then we can multiply both sides by b and d to get this equivalence relation. And we'll also define this inequality, which we'll need to use if we want to show that the rational numbers are an ordered field. This is where we get this inequality definition. It means that this fractional inequality is satisfied. We'll also only use this inequality with fractions when they have a positive denominator. This should be enough to properly define it, since these fractions with positive denominators can always represent the fractions with negative denominators. So a rational number is equal to this equivalence class, which includes all of the ordered pairs of integers that are equivalent to each other, so that the fractions that they represent are equal to each other. But fractions don't exist yet, but we can use the equivalence relation to say that they would be equal to each other if they were fractions. This is an example of an equivalence class. All of these ordered pairs of numbers have the same ratio and would be equal to each other if they were expressed as fractions. This is also a good notation for expressing equivalence classes in bar notation, but we won't be using it here. To show that the two equivalence classes are equal, that is, that they contain all the same elements, it is only necessary to show that these numbers are equal. In fact, it is only necessary to show that these two ordered pairs are equivalent. So when we prove that the rational numbers are a field, or that this relation is an equivalence relation, we only have to show that two classes are equal by showing that they are equivalent. So now to define multiplication in this set. These two ordered pairs multiplied together are equal to this ordered pair. It is based on this multiplication between these two fractions that they represent. And now we can define addition to be this, which looks more complicated than multiplication. It is based on the addition of these two fractions. To add them, we have to multiply them by these fractions that are equal to 1, so that their denominators become equal. So then we are left with these two fractions that are easy to add because they have the same denominator. And then we can move everything onto one bar. So this is what addition in this set represents. So now we have to show that this equivalence relation that we have defined really is an equivalence relation. We have to show that it satisfies reflexivity, which means that any number in the set has to be equivalent to itself. And it obviously is, because it satisfies this equivalence property that we have defined. We have to show that it is symmetric, so a statement is true if the two sides of the equation are swapped like this. So this is true because this equation can be swapped around the equal sign. Now to prove the transitive property, which is expressed like this. This should divide the set into large chunks of elements that are all equivalent to each other and not equivalent to anything else. We can get these two equations from the first part of this transitivity statement. we can multiply them together to get this equation. We can rearrange them like this so as to get it into the final form that we want. After dividing this equation by this number, we'll get this equation, which can be packed back up into this equivalence statement, which proves transitivity. So this relation is an equivalence relation. So now we can prove that the rational numbers form a field. We'll do this by showing a lot of different things. First of all, we need to show that both 1 and 0 are in the set. We'll start off with 0, which looks like this. Now we have to show that it is a 0 by adding it to an arbitrary number in the set. We'll substitute this number 0 into the variable z like this. Then we'll add these two numbers up using the addition rule, then simplify it. And this final number is equivalent to the number before 0 was added to it. So this number really is 0. And here's a short proof showing that these two numbers are equivalent if we multiply them out according to the equivalence rule. Now we have to show that 1 is in the set. This is what 1 is equal to. 1 behaves the same as 0, but for multiplication instead of addition. We'll look to see if this number behaves like 1 by multiplying it by an arbitrary number in the set. We'll substitute this value for 1 into this equation, and it is very obviously equivalent to the number that we started with before we multiplied it by 1, so 1 is in the set. Now to prove closure, we'll prove it for addition. Manipulating this equation gives us an ordered pair of two integers, which is still in the set. We'll have to prove closure for multiplication. And so closure is true for multiplication. So the closure axiom has been proven true for this set. So now to prove associativity true for this set, we have to swap the large brackets over to the last two numbers, so as to show that the order that these operations are done in doesn't affect the result. So we can apply the addition rule twice to get this number, and then apply the addition rule twice in reverse, so as to complete the bracket swap. So associativity for addition has been proven true. Now to show associativity for multiplication, which is nearly the same as for addition, we can use the multiplication rule to get this number, and use this rule in reverse to prove this axiom true. Now to show that commutativity is true for addition, that is, that it doesn't matter which sides of the plus sign that the numbers are on. And so we can expand and contract this expression with the addition rule to show that the commutativity axiom is correct for this set. Now to show that every number in this set has a negative or opposite, and this is what it is. And now to see if it behaves like an opposite, we'll add a number in the set to its opposite. They both should add together to make 0. And after using the addition rule, we find that it is equal to a number that looks like it could be 0. And it is equivalent to a number that we've defined to be 0, so this axiom is correct. Now to test the distributivity axiom, we'll start with this expression. We'll expand it with the addition and multiplication rules to get this number, and it's equivalent to this number. And after manipulating it and using the addition and multiplication rules, we finally arrive at this expression, which proves the distributivity axiom correct. All of this has now proven this set to be a ring, but we can take the final step and prove it to be a field. We have to prove that all non-zero numbers in this set have an inverse, and this is what it is. We'll multiply these two numbers together to see if it behaves like an inverse. We get this number which looks like it could be a 1. And it is equivalent to the definition of 1, so this proves this axiom correct. And so this is a field. We can plug any number into any equation involving addition and multiplication and get a number back. So these are the definitions for less than and equality. Two fractions are equal if they are equivalent according to the equivalence relation. We can also define the greater than relation in a similar way as for the less than relation, when these two fractions have this relation. We can take the next step and prove that this set is an ordered field. We have to prove all of these axioms to do this. There's this irreflexivity axiom which says that any element can't be greater than itself. I've never seen this symbol before, the not greater than symbol. So to prove irreflexivity, it only needs to be shown that the two numbers are equal. Now to prove trichotomy, which means that any particular number can only be less than, greater than, or equal to another particular number. We'll set all of the denominators to always be positive, so as to prove this without loss of generality, that I've abbreviated to WLG. You'll always find an element of an equivalence class with a positive denominator. So we'll prove each of these cases to prove this axiom. These could be taken to be definitions of greater than or equal to. We've taken them directly from these numbers in fraction form. These three cases cover every possibility for any pair of numbers. We'll prove this particular addition axiom. We'll start with this equation and try to work our way to the final equation that we want. We'll perform this multiplication, and then this addition, and work our way through the algebra to get equation 13, which we can pack up into the inequality that we want, thus proving this axiom. Now to prove this multiplication inequality, we'll start off with these two equations. We'll set all of the denominators to be positive. We'll unpack the second equation to get this integer equation. Then we'll make this substitution to get this inequality, saying that this number is positive. We'll similarly unpack the first equation. We'll multiply this equation by this number to get this equation. We can then pack this equation up into this inequality. Then we can use the multiplication rule in reverse to get this equation, which proves this axiom correct. Now the final axiom to prove is transitivity, which is the longest to prove, so that's why I left it until last. We'll set all of the denominators to be positive and use the definitions to get these integer equations. We'll look at all three cases separately. Looking at the case when C is positive, then E must be positive, because EF must be positive to be greater than CD. We can then multiply both sides of the equation by a positive number, resulting in this equation, and then we can use the definition to get equation 3. We can divide both sides by a positive number to get this equation. Using the definition in reverse, we can prove that transitivity is true for this case. In this second case, C is negative, and then A must also be negative to make up a number less than 0 with a positive denominator. Multiplying the two equations together is multiplying them by a negative number, so that the sign is flipped. Dividing the equation by this number causes the sign to flip again, and so using the definition we get this inequality. So now in this third case, when C is equal to 0, A must be negative to be less than 0, and E must be positive to be greater than 0, so E must be greater than A. In fact, if we multiply these two numbers by any positive numbers, this inequality will still be true, because the left-hand side will be negative and the right-hand side will be positive. So this inequality will be true again, so we've proven transitivity true for this field. So the rational numbers form an ordered field, so that we can place all of the numbers on a number line, with some numbers being larger than other numbers. This is what the rational numbers look like. All of these numbers are sets of points along straight lines through the origin. Some of these numbers like 1, 2, and -1 are shown as the points in these bounded regions. So I hope you have enjoyed this video and have learnt a lot from it. I decided to prove some of these theorems jumping 2 or more lines at a time. If you'd like me to produce another video with slower versions of these proofs, then please let me know in the comments. Click like and subscribe if you enjoyed this video and felt that it helped you, and thanks a lot for watching.